The research paper delves into the stability of solitons in a 3D Maxwell Lorentz system with a spinning particle. It explores solutions that describe a particle moving with a constant velocity and rotating with a constant angular velocity. A key finding is the orbital stability of moving solitons with zero angular velocity, as well as the linear orbital stability of rotating solitons with zero velocity. The Hamilton Poisson structure of the system is degenerate and admits Casimir invariants, which are utilized to construct a Lyapunov function. A pivotal aspect of the research is establishing a lower bound for this function, achieved through angular momentum conservation and spectral arguments. These include the Heinz inequality and the closed graph theorem. In the realm of theoretical physics, the stability of solitons in the 3D Maxwell Lorentz system has garnered significant attention. This paper delves into an extended charged spinning particle, where its motion is dictated by the interplay between electric and magnetic fields, position, momentum, and angular velocity. The dynamics of this system are governed by the Maxwell and Lorentz equations, ensuring the conservation of mass and angular momentum. The stability analysis of solitons in this context is paramount, as it sheds light on the orbital stability of these particles. To achieve this, the Lyapunov function is employed, providing insight into the system's stability. Furthermore, the Hamilton Poisson structure and the canonical transformation to the comoving frame are explored, offering a comprehensive understanding of the system's dynamics and stability. This research contributes to our understanding of the intricate dance between electromagnetic forces and particle motion, providing valuable insights for researchers in the field of theoretical physics. The findings of this study could potentially impact future investigations into soliton stability and the behavior of charged spinning particles in various contexts. The system under consideration is a classical model of an extended electron, introduced by Abraham in 19,031,905. This model describes the dynamics of a spinning particle coupled to its own Maxwell field. It is defined by the equations of motion for the particle's position q, t, and angular velocity omega, t, as well as the electromagnetic fields E, x, t, and B, x, t. The velocity field W, x, t, is defined as the sum of the particle's velocity and the angular velocity of the particle's rotation. This model has a rich history, having been used to describe the classical Landé model of spin in old quantum mechanics and to explain radiation damping in classical electrodynamics. The system has also been studied in the context of non-relativistic quantum electrodynamics, QED. The charge density ρ, x, is assumed to be smooth, spherically symmetric, and non-zero, with support in a ball of radius r ρ. The system is invariant under the Euclidean group generated by translations, rotations, and reflections of r³. A key feature of the system is the existence of solitons, discovered by Spohn, which are solutions moving with constant speed v and rotating with constant angular velocity omega. These solitons exist only for parameters v, omega, in a specific set sigma, which is characterized by the condition that the speed v is less than 1 and the angular velocity omega is either parallel or perpendicular to versus in the special case where ρ, x, is identically 0. The system reduces to a trivial case where the particle moves with constant velocity and the Maxwell equations decouple from the particle's motion. In this case, the energy of the Maxwell field is conserved, and so are the particle's momentum and angular momentum. The orbital stability of solitons SV, 0 with v less than 1 is ensured by reducing the system to the comoving frame and establishing a lower bound for the Hamiltonian as a Lyapunov function. In contrast, the stability of S0, omega is proven through the conservation of angular momentum j, focusing on initial states with zero total momentum. The linear orbital stability is demonstrated by constructing a Lyapunov function for the linearized equations, guaranteeing a lower bound for the function. This approach is analogous to the energy Casimir method. The Maxwell Lorentz system, a fundamental model in classical electrodynamics, describes the interaction between a charged particle and the electromagnetic field. This system consists of two equations, one governing the evolution of the electromagnetic field and the other describing the motion of the charged particle under the influence of the electromagnetic force. The system has been extensively studied, yielding significant findings on solitons, radiation damping, and the asymptotic stability of solitary manifolds. The Wiener condition, expressed as ρ k equals 0 for k element of R cubed, has played a crucial role in many of these studies, ensuring a strong coupling between the charged particle and the eigenfunctions of the continuous spectrum of the free field. Researchers have utilized this condition to prove the global attraction to stationary states, radiation damping, and the asymptotic stability of solitary manifolds for the Maxwell Lorentz system in various dimensions. In the context of spinning particles, the global convergence to rotating solitons has been established under certain conditions, such as a particle at rest with a sufficiently small charge density or without this assumption, provided the particle mass does not belong to a discrete set of resonances. However, the stability of solitons for the Maxwell Lorentz system with moving and spinning particles remains unexplored. To address this, the concept of the Maxwell potentials and their relationship with the electromagnetic fields through the Coulomb gauge is introduced. By applying the orthogonal projection P, the gradient term can be eliminated, paving the way for further analysis of the system's behavior. The well-posedness of the system is also discussed, with the Coulomb potential derived from the second equation in the system, setting the stage for a deeper exploration of the system's dynamics, particularly concerning the stability of solitons in the presence of moving and spinning particles. The mathematical framework for the dynamics of a charged particle interacting with a Maxwell field is derived from divergence-free vector fields, utilizing the current density and the particle's motion. This system of equations involves the particle's position, velocity, and angular momentum, along with the electromagnetic field. Formulated in terms of Hilbert spaces F0 and F1, the spaces Y and V are defined to describe the system. Basic operations are denoted and the momentum and angular momentum of the particle are defined. Proposition 2.3 states that the system admits a unique solution for any initial state, and that the solution map is continuous in the specified Hilbert spaces. This proposition provides a foundation for understanding the behavior of charged particles in electromagnetic fields, which is crucial in various fields such as quantum mechanics, particle physics, and electromagnetic theory. The refined version of the transcript begins directly with the content, maintaining a highly technical and professional tone. It uses precise language and domain-specific terminology, ensuring technical accuracy and depth without any introductory phrases or concluding remarks. The energy functional, 2.9, is reformulated as a Hamiltonian functional, h, a, pi, q, p, pi, defined on the Hilbert phase space y, as specified in 2.5. This functional is decomposed into kinetic and potential energy terms, involving the variables a, pi, q, p, and pi. The resulting system, 3.1, admits a Hamilton Poisson representation, characterized by the Hamiltonian vector field y, which is the product of the skew-symmetric operator j, y, and the gradient of the Hamiltonian functional dh, y. The explicit form of j, y, is provided in 3.3, which is not invertible for all y expansion of the system. 3.3 yields the dynamical equations for a, pi, q, p, and pi. Notably, the system conserves the Casimir invariants c, y, equals pi squared, which are demonstrated to be time invariant by computing the time derivative of c, y, and exploiting the skew symmetry of j, y. Subsequently, the paper discusses the canonical transformation to the comoving frame, where a and pi are rewritten as a, y, t, and pi, y, t, by shifting the spatial argument by q, t. The variables in the system, 3.3, are then transformed via the map t, which replaces the momentum p with the conserved total momentum p, defined in 2.10, and rewritten in terms of a, pi, and q using 2.6. The paper explores the equivalence of two systems, one defined by equations, 3.3, and another by equations, 4.5, within a Hamiltonian framework. A pivotal insight is that the map defined in equation, 4.2, is canonical, maintaining the canonical form. This is demonstrated through the identity in equation, 4.6, which simplifies to a known expression when utilizing equation, 4.3. The equivalence of Lagrangians and their corresponding actions is also established, implying that the solutions of both systems are interconnected. The Hamiltonian, 4.4, does not depend on the variable q, leading to simplified equations for q and p in the system, 4.5. Consequently, the system reduces to a family of Hamiltonian systems with parameter p, described by equations, 5.2. This reduction is significant, as it simplifies the analysis and potentially uncovers new insights into the behavior of the system. The authors develop a Hamiltonian formulation of the reduced system, where the Hamiltonian J, Z, is a 3×3 matrix defined on the reduced phase space Z equals A, pi, pi. The reduced Hamiltonian HP, A, pi, pi, is composed of three terms: the energy density of the electromagnetic field, the kinetic energy of the particle, and the interaction energy between the particle and the electromagnetic field, as described in equation 5.4. The system of equations, 5.5, is derived from the Hamiltonian Hp, Z, governing the time evolution of the electromagnetic potential A, the canonical momentum π, and the particle's position π. The velocity versus t and angular velocity omega t are defined in equation 5.6 as functions of the canonical momentum and the electromagnetic potential. The Hamiltonian Hp, Z, is well defined and Frechet differentiable on the reduced phase space Z, a direct sum of the spaces F1, F0, and R3, as described in equation 5.7. Furthermore, the Hamiltonian is conserved along the trajectories of the system, 5.5. The authors then calculate the solitons of the system, which are solutions of the form SV, omega, t, equals, avenue, omega, xvt, pi v, omega, xvt, vt, pv, pi v, omega. The momentum pv and the canonical momentum pi v, omega are derived from equation 3.1 and definition 2.7, as given in equation 6.2. The corresponding conserved total momentum pv, omega, is given by equation 6.3, derived from equation 2.10. In the comoving frame, solitons become stationary solutions of the reduced system, with conditions that imply the existence and uniqueness of solitons under specific velocity and angular momentum pairs. These solitons are characterized by their Fourier transform, which depends on the velocity and angular momentum, as well as the density function. The effective moment of inertia for these solitons is greater than the initial moment of inertia, and they only exist for certain velocity and angular momentum combinations. Outside these conditions, solitons do not exist. The authors present a lemma that represents total momentum, PV, omega, in terms of an effective mass MEF, which is a continuous function of v and omega. This is given by equation 6.11. They then formulate the definition of orbital stability for solitons, which are solutions to the system, 3.1. A distance metric, d, y, t, sv, omega, t, measures the difference between a solution y, t, and a soliton sv, omega, t, in terms of reduced trajectories, defined in equation 6.12. A soliton is considered orbitally stable if, for any positive r, there exists an epsilon such that d, y, 0, sv, omega, 0, less than epsilon implies d, y, t, sv, omega, t, less than r for all t in r. This definition is given in definition 6.5. In the case where ρ, x, is identically 0, all solitons are orbitally stable, as stated in remark 1.1. The authors then discuss the construction of a Lyapunov function, lambda, z, which is an invariant of the system and admits a lower bound. This lower bound is given by equation 7.1, stating dl is greater than or equal to kappa, ba nabla dbl delta z, ba nabla dbl 2z for some positive constant kappa, v. They propose constructing the Lyapunov function as a perturbation of the Hamiltonian HV, omega by a suitable Casimir invariant. The variation of the Hamiltonian, delta HV, omega, for a perturbation delta z equals alpha, y, beta, y, gamma, in z, where div alpha, y, equals div beta, y, equals 0, is calculated in equation 7.2. The calculation of the variation in Hamiltonian, delta HV, omega for a system with a perturbation in the magnetic field and a perturbation in the velocity field is discussed in this section. This calculation is based on equations 2.2, 6.3, and 6.4 derived from previous pages. The variation in Hamiltonian is expressed as delta HV, omega equals J1 plus J2, where J1 represents the integral of the square of the magnetic field perturbation and the curl of the electric field perturbation, along with a term representing the interaction between the magnetic and electric fields. J2 is a combination of terms related to the changes in momentum and angular momentum due to the perturbations, as well as a term involving the magnetic field perturbation and the vorticity of the velocity field. After rearranging and simplifying the expressions for J1 and J2, the final expression for delta HV, omega is given by equation 7.7. This equation shows that the variation in Hamiltonian is a sum of three main components. The first term represents the energy associated with the magnetic and electric field perturbations. The second term represents the kinetic energy change due to the momentum perturbation, and the third term represents the energy change related to the angular momentum perturbation and the interaction between the magnetic field and vorticity. The Hamiltonian's first term, J1, admits a lower bound, given by equation 7.8, a key result in analyzing soliton orbital stability when omega equals 0. In this case, solitons SV, 0 are critical points of the reduced Hamiltonian HV, 0, satisfying identities, 8.1. The last identity in 8.1 follows from equations 5.4 and 6.2, enabling the Hamiltonian to be considered as a Lyapunov function. Lemma 8.1 provides a lower bound for the Hamiltonian variation delta HV, 0, given by equation 8.3, a crucial step in establishing orbital stability. The proof relies on inequalities 7.5, 7.6, with omega equals 0 and the Cauchy-Schwarz inequality, yielding equation 8.4. The main result of this section is theorem 8.2, stating that soliton SV, 0 is orbitally stable under conditions 1.2 and v less than 1. The proof involves a modification of the general scheme presented in prior work, leveraging the established lower bound for the Hamiltonian variation to demonstrate orbital stability. This refined version maintains the technical accuracy and depth of the original content while condensing the information into a concise and direct form suitable for voiceover narration. The conservation of the Hamiltonian's principal part, Hp, Z, T, is guaranteed for the system with parameter p, implying a bounded deviation from Hp, Sp, of at most epsilon 1, which vanishes as epsilon approaches 0. Furthermore, a lower bound is established for the difference Hp, Sp plus delta Z, minus Hp, Sp, proportional to the norm of the gradient of delta Z with respect to the banorm, where delta Z is the initial deviation from the steady-state Sp. Combining these results with the convergence of Z, T, to Sp and Sv, 0 as epsilon approaches 0, we deduce that the subnorm of Z, T, minus Sv, 0 converges to 0 uniformly in time. Moreover, the terms on the right-hand side of equation 6.12 are uniformly small in time, as a consequence of equations 5.6, 8.5, and 8.8. The discussion then turns to the conservation of angular momentum for the reduced system with p equal to 0. This is facilitated by the Lyapunov function lambda v, omega, z, equals hv, omega, z, minus nu f2 pi 2, where nu f is defined as the reciprocal of the effective moment of inertia if. In the reduced system, the function serves as an invariant, with its critical points being the solitons SV, omega. However, the presence of the negative term in the expression hinders the establishment of a lower bound of type 7.1. To overcome this, we introduce an additional invariant, the angular momentum, which is conserved in the system with zero total momentum. Considering the system 3.1 with p equals 0, we derive the reduced system 5.5 and the angular momentum conservation equation 2.13 with p equals 0. For stationary solutions, the solitons SV, omega with v equals 0, the angular momentum becomes a constant. The Hamiltonian, 5.4, with p equals 0 is also derived, which represents the energy of the system. Notably, the set Z infinity 0 is dense in Z, and a lemma is stated for solutions to 9.3, with initial states in Z infinity 0. This lemma provides a crucial insight into the behavior of the system, facilitating further analysis and understanding of the solitons SV, omega. The stability of solitons in a nonlinear system is discussed, focusing on the conservation of angular momentum and the definition of a tangent space for a specific manifold. The requirements for soliton stability include conditions on the magnetic field A, X, T, and its derivatives. The conservation of angular momentum leads to the introduction of the manifold M omega and its tangent space T omega, defined as a closed linear subspace of codimension 3 in Z0 with an orthogonal projection P omega onto it. The representation of T0 omega and its relationship to Z0 are also presented. The linearization of the reduced system at the soliton S omega is performed, resulting in the variational equation xi T equals df S omega xi T. This process allows for the calculation of the Hamilton Poisson structure for the linearized dynamics, focusing on linear terms in xi. The quadratic part of the Hamiltonian h omega xi is used, including terms up to quadratic order. The linearization of the dynamics is then applied to the equation for gamma t, leading to the equation gamma t equals minus npo and gamma minus and b nabla acatly tie and alpha rho y and b nabla acat nabla I ht minus gamma and omega. This equation forms the basis for the stability analysis of the linearized dynamics in the tangent space. The linearized equation 10.3 is rewritten as equation 10.8, describing the dynamics of the tangent space T omega. To prove the invariance of T omega with respect to the linearized dynamics, lemma 10.1 is introduced, stating that the vector field df S omega xi is tangent to T omega for any xi in Z. This is proven by differentiating the angular momentum conservation equation 9.4 and using the density of Z infinity 0 in Z. The main result of the paper, presented in theorem 10.2, establishes the stability of the linearized dynamics. Specifically, it shows that for any initial condition xi 0 element of T omega, there exists a unique solution xi T element of C R T omega to equation 10.8, and the map xi 0 right pointing arrow xi T is continuous in T omega for T element of R. The theorem also provides a uniform bound on the norm of the solution, given by equation 10.12. The proof relies on an a priori estimate derived using an energy functional, chosen as the quadratic part of the Lyapunov function 9.1, with v equals 0, denoted by L omega xi in equation 10.13. The conservation of this functional under the linearized dynamics ensures the stability of the system. Differentiating the Lyapunov function L omega with respect to time, we obtain equation 10.14 by applying equations 10.7 and 10.8. This equation simplifies to 0, indicating that the Lyapunov function L omega is conserved. This conservation is further supported by proposition 10.3, which states that the Lyapunov function L omega admits a lower bound, as expressed in equation 10.15. The calculation in equation 10.14 shows that the linearized Lyapunov function is conserved, whereas the terms h omega, xi, and nu f gamma 2 are not. This is in contrast to the case of the nonlinear Lyapunov function, where both terms are conserved quantities. The next section focuses on proving the lower bound for the Lyapunov function on the tangent space. A stronger bound, expressed in equation 11.1, is proven for the quadratic form Q rho. This bound is continuous on the Hilbert space T omega and suffices to prove it on the dense subspace of smooth functions T infinity omega. The bound can be rewritten as equation 11.2 for smooth functions, where Q rho and Q0 are defined in equation 11.3. The properties of the operator Q rho are discussed, focusing on its non-negativity and injectivity. The positive definiteness of Q0 and its self-adjointness in the domain Z0 are established. The common domain of Q and Q0 is identified as Z infinity 0, which is dense in Z0. The non-negativity of Q is asserted, with its kernel having dimension 3, intersecting with T0 omega only at 0. The proof involves the restriction of Q and Q0 onto T infinity omega, where the operators are expressed as non-negative self-adjoint operators Q and Q0. The inequality Q is greater than or equal to micro Q0 is demonstrated with sufficient small micro greater than 0, proven by showing the boundedness of the operator Q0 Q-1 rho. This boundedness is ensured by the finite rank of the difference Q minus Q0 in Z0, and thus in T0 omega. The positivity of the Lyapunov function on the tangent space is a crucial step in establishing the stability of a system. The authors focus on proving proposition 11.1, which involves demonstrating that the operator B is non-negative for all y and y infinity. They utilize the Heinz inequality and the properties of the Laplacian operator in the invariant space F0. The authors begin by showing that the bound, 11.8, holds, which implies the bound, 11.2, with kappa equals micro. This result eliminates the point spectrum at 0 of the operator Q in the tangent space T0 omega. The application of the Heinz inequality helps establish the equivalence of continuous spectra of Q and Q0. Next, the authors proved proposition 11.1 by demonstrating the non-negativity of the operator B for beta equals 0. This is achieved through the calculation of the kernel of the resolvent R, lambda, equals B lambda, caret 1, which reduces to a finite-dimensional problem. The equation, B lambda, y equals 0 with y equals, alpha, gamma, element of D, B, is solved, leading to a system of equations, 12.4, that must be satisfied for the kernel to be 0. The authors aim to show that this system has no non-trivial solutions, thus proving the non-negativity of B and completing the proof of proposition 11.1. The authors rewrite the first equation using the last equation, resulting in equation 12.5, which is then transformed into the Fourier domain, yielding equation 12.6. This equation holds for lambda equals 0, as the term m asterisk operator minus I nabla rho 0 equals 0. The vector field m asterisk operator x rho x w is divergence-free due to spherical symmetry. Substituting equation 12.6 into the second equation of 12.4, the authors obtain equation 12.7, which defines the matrix A, lambda. Since A, lambda, is Hermitian for lambda is less than or equal to 0, it is uniquely defined by its quadratic form, which is expressed in terms of the Fourier transform of the density ρ. The quadratic form is then simplified, resulting in equation 12.8, which is equivalent to the original equation 12.3. The functions a minus, lambda, and a plus, lambda, are strictly increasing and decreasing, respectively, for lambda is less than or equal to 0, and both are continuous. Hence, equation 12.8 holds, as a minus, 0, equals a plus, 0. The authors then proved proposition 11.1, stating that the non-negativity of equation 11.4 follows from lemma 12.1. The kernel of the operator Q is characterized, and its dimension is shown to be 3. Finally, the intersection of the kernel of Q and the subspace T0 omega is proven to be 0. The authors discuss the implications of the lower bound for the quadratic form Q on the tangent space for the Lyapunov function lambda 0, omega, highlighting that their method of proof reduces the problem to calculations with differential operators, avoiding pseudo-differential operators. They also explore the orbital stability of solitons SV, omega with omega does not equal 0 and v less than 1, proposing the solitary manifold S as a global attractor and the submanifold S, barred BL, as asymptotically stable. The authors prove lemma 6.2, involving calculations for soliton parameters, and consider two cases for omega and v, deriving equations for pi v, omega and expressing it in terms of the effective moment of inertia I, barred BLF, and the integral of nabla rho k 2 over k. The proof of lemma 6.2 is crucial for establishing the main result of the paper. It is divided into two cases: when the vectors v and omega are perpendicular, and when they are not. In the first case, the authors derive expressions for qv, omega and pi v, omega using Fourier transforms and the properties of ρ, x. They show that I up tac E greater than I, barred BLE for ρ, x, is defined as 0, as stated in remark b.1. In the second case, where v and omega are not perpendicular, the authors calculate qv, omega and pi v, omega again using Fourier transforms. They demonstrate that alpha 1 greater than alpha 2 for v less than 1, leading to the conclusion that I up tac E greater than I, barred BLE. The final section addresses the density of C infinity 0 in the space of divergence-free vector fields, F0. The authors introduce a sequence of functions bm, k, and bm, k, and prove that bm, k, converges to a, k, as m right pointing arrow infinity. This implies that the corresponding functions am, n in the physical space converge to a in L2, establishing the density of C infinity 0 in F0. The research paper establishes the existence of a subsequence am, n, m, in L2, which converges to Oz as m approaches infinity. This subsequence is characterized by its membership in C infinity 0 and the property that divm, n, x, is equivalent to 0. The page primarily consists of a list of 16 equations, each representing a key step in the proof or an essential property of the subsequence am, n, m. These equations are crucial for understanding the convergence and properties of the subsequence, as they demonstrate the technical details underlying the main claim. The paper's focus on this subsequence contributes to a deeper understanding of the behavior of sequences in L2 and their convergence properties, particularly in relation to the function Oz. This work has implications for various areas of mathematics and physics, including functional analysis and partial differential equations. The authors present a detailed compilation of key findings and methodologies in their research paper, focusing on the comprehensive list of techniques and principles that have been explored. This section highlights the extensive work conducted to identify and analyze various factors influencing the subject matter. The paper delves into the intricacies of theoretical frameworks, providing an in-depth examination of how different models can be applied to understand complex phenomena. By dissecting these models, the authors demonstrate their applicability and limitations within specific contexts. Moreover, the paper explores various methodologies used in data collection and analysis, emphasizing both qualitative and quantitative approaches. It discusses the importance of triangulation, where multiple methods are employed to validate findings and enhance the reliability of results. The authors also delve into statistical analysis, detailing various tests and measures utilized to identify trends and patterns within datasets. They emphasize the importance of statistical significance, highlighting how it can inform conclusions drawn from empirical data. Furthermore, the paper touches upon ethical considerations in research, underscoring the need for researchers to maintain objectivity and avoid bias. It discusses the importance of informed consent, confidentiality, and privacy protection, particularly when dealing with human subjects. In conclusion, this section of the research paper serves as a valuable resource for researchers seeking to understand the breadth of methodologies and principles available for their own investigations. By providing a detailed overview of theoretical frameworks, methodologies, statistical analysis, and ethical considerations, the authors aim to equip researchers with the tools necessary to conduct rigorous and reliable studies. The final page of the research paper presents a comprehensive list of references, providing an extensive overview of the sources used in the study. This section is crucial for maintaining academic integrity and allowing readers to delve deeper into the topics discussed throughout the paper. The references are organized in a systematic manner, following the chosen citation style. Each entry includes essential details such as the author's name, publication year, title of the work, and publisher information. This structure ensures that readers can easily locate and access the original materials, facilitating further exploration and validation of the research findings. Moreover, the reference list serves as a testament to the thoroughness of the research conducted. It demonstrates the author's commitment to consulting a wide range of credible sources, from seminal works to recent studies, in order to build a robust foundation for their arguments and conclusions. In addition to academic journals and books, the reference list may also include conference papers, technical reports, and online resources. These diverse sources reflect the multidisciplinary nature of the research, highlighting the importance of interdisciplinary collaboration and knowledge sharing in advancing scientific understanding. The inclusion of a detailed reference list also underscores the importance of transparency and reproducibility in research. By providing a clear trail of the sources used, the authors enable other researchers to replicate their study, verify their findings, and potentially build upon their work. In conclusion, the final page of the research paper provides a valuable resource for scholars and practitioners alike, offering insights into the breadth and depth of the research conducted. It serves as a springboard for future investigations, encouraging continued exploration and innovation in the field.